We're going to be taking a look at acids and bases today. This is going to be section 19.1. Hopefully you guys got the lab done, which was lab on household acids and bases. And what that looks at is the pH and things that are acids and things that are bases. We also did these litmus tests, which we're going to be doing in this demonstration as well. And if you remember, the red rhymes with acid, and B starts with, our base starts with B, and so that's looking at the coloration of blue. So we'll get to this demonstration in a little bit. So first of all, let's take a look at things that are acids. These are from the lab that we did, and vinegar is an acid. If you've ever tasted vinegar, it is acidic. And the name of vinegar is acetic acid. We may be doing a lab with vinegar, acetic acid, to calculate the percentage of acetic acid that is in your vinegar that you can buy from the grocery store. Lemons are also acidic as well, and you might know the name that is found in lemons and limes and in oranges. These are all citrus fruits, and so this acid is called citric acid. And even carbonated beverages, when you take H2O and you combine it with CO2, you get carbonic acid. So these are some common examples of acids. The flavor of acids. We have 4 receptors on our tongue. We can taste sweet, sour, salty, and bitter. There is a 5th taste recently discovered that's in the very back of your throat, but these are the common 4. And the flavor of acids is going to be sour. Now here's where one of the demonstrations is going to come in. We're going to be taking a look at our acids and our bases. If you remember, we did this with the these little probes here, and if we connect them, okay, we get our loud noise. Well, let's go ahead and we're going to test to see, do acids conduct electricity? Because I have this all connected to a battery. Here comes the battery. Here's the battery, and here's all the connections, and that's connecting to the cord over there, which connects to the buzzer. So when I contact them, it's going to be making some noise. So if I contact this with the acids, you see that it makes noise. If I contact with the bases, it also makes noise. Whoa, it makes some noise as well. So the reason is that there is something inside of the water that is conducting the electricity. And for acids, it is the H+. So acids are electrolytes. They conduct electricity. They conduct electricity. And the reason why they conduct electricity is because they have the H+. So it's charged. It enables the charge to be transmitted. We saw in the last lab it reacts with dyes. Okay, and the main concept of this is we have this red coloration and we have the blue coloration. So let's go ahead and take a look at this again. So there is a stain inside of this litmus paper right here. So this litmus paper is red. And so I want to show you, if I dip it into something that is acidic, it is going to stay red or kind of pinkish in color. If I take this and put it into the base, okay, it's going to change into a bluish color, and vice versa. If I take the litmus paper that tests for base and I put it into the base, it's going to stay purple, okay, and if I put this into the acid, things that are acidic are going to turn red. And so that turns a bright red. So that's because of the stain that's inside. So here I have a red sponge, and what I'm going to do is I'm going to put this into the acid. Remember, things that go into acids are going to turn red. So if I put this inside the acid, whoa, that doesn't turn red. Kind of turns a bluish, dark bluish color. What's interesting though is if I take this, and if I just squeeze this out, it comes out red. But if I take this and if I put this into the base, which is blue, it turns my sponge back into a red. But what's interesting is if I squeeze that out, it comes out to be blue. What in the world's going on here? So what's happening with these stains is that they are changing their shape. The H plus or even the OH minus has the capacity to bind onto the stain. So acids, what they do is they react with these dyes or these stains. The main concept of this is that the stain changes shape. When it reacts with the H plus physically binds onto it. The stain changes its whole molecular shape. And because the stain changes shape, it's then going to change its color. So imagine that this is the shape of the stain. And then you add an acid to it, and the acid has the capacity to bind onto one of these regions right here, and then it changes this into something like that. So when this stain right here, here's the molecular shape of the stain, when you add the acid or the H+, it actually changes the shape. When it changes that shape, it actually reacts to light differently. So main concept is when a stain changes its shape, it's going to be changing its color. So what is going on right here? Well, if you have the litmus paper, okay, here's the litmus. If you remember the pH ranges, we did this on our household acids and bases, between 0 and 14. And again, 7 is right in the middle. And for litmus paper, here's your acids down here, and here's your base. So again, your acids range between 0 and 7, and your bases range between 7 and 14. The litmus paper, what this does is it turns red if you're between 0 and 7. If you're in a base, it's going to turn blue. Why was my red sponge turning blue when I added it to the red acid? The reason that it changed color is that within this sponge, this is actually not made out of litmus stain. There is another stain that is on the inside of the sponge, and that sponge is called Congo red. And so here we have the pH scale between 0 and 14 again, except when you take Congo red and you put it into an acid, it turns blue. And the sponge, once it was blue, if I turned it or put it into the base, it turned red. And again, it's based upon the stain. Every stain has a different shape, every stain has a different color. When you change that shape, you change the color. One of the distinguishing characteristics of acids is these react with metals. For example, we've done labs last semester where we put magnesium into hydrochloric acid, and we put calcium into hydrochloric acid. Those react with metals. So those are our acids. Now let's take a look at our bases. Some examples are baking soda, detergent, and bleach. If you'd like, you can go into your cabinet at home and just take a very, very small taste of baking soda. Just put a little bit on your finger and then put it in your mouth and then taste it. Please don't do that for bleach or detergent, but you can do that for the baking soda. And what you would taste is bitter. Now, pancakes and muffins are made out of baking soda. If you've ever made pancakes before and made a mistake on the baking soda, if you put too much baking soda, it almost tastes like metal. It's very, very bitter. Very similar to the electrolytes up here, these bases, these OH minuses, are going to conduct electricity. So it's the OH minus that helps to conduct the electrical charge or the electricity. These also react with indicators. Remember, the Congo red can react between 0 and 14, and the litmus can react between 0 and 14 as well. They both can react in the base range. And one of the distinguishing characteristics of acids and bases is going to be that they are slimy. They are slimy feeling. And if you remember, we created a molecule called soap by taking coconut oil and mixing it with a compound called sodium hydroxide, or NaOH. And soap is primarily slimy because it has the base OH in it. So that's acids, and those are some characteristics of bases. What I want to look at now is taking a look at something that's neutral, and that's water. And a lot of people think that water is neither an acid nor is it a base. But actually, it is both an acid and a base at the same time. Take a look at the water molecule. We have H, O, and H. If you were to cut this right here, we have one H plus and we have one OH minus. We could bring those two back together and create water, but water is created up of acid and base. And if you have something that's neutral, you do not lack acid and base, you have something that has an equal amount of H pluses and OH minuses. So water is both an acid and a base, which makes it neutral. So imagine that you have a water particle. Here's going to be an H2O. And this actually happens on a very small scale all the time. While these water molecules are have these hydrogen bonds between them, they're running around each other, they're rolling around each other. We have two water particles. Sometimes they actually bump into each other. So this is going to bump into this over here. Two water particles are going to bump. And what happens is it transfers the hydrogen. So what does it look like? And what is the name of this? It will look like this, but it's going to have 1, 2, 3 hydrogens. And it's going to be H3O plus. Well, if we transfer the hydrogen over here, what we're left with is the oxygen and 1 hydrogen. We're going to be left with this over here, which is the OH minus. These each have names, and you're probably familiar with the OH minus. This is called the hydroxide ion, like sodium hydroxide. So it's important to know these ions, these names. Hydroxide ion, we've seen this before also when we created these ionic compounds from last semester. We haven't seen this one before though. The name of this one is the hydronium ion. So we have the hydroxide ion and the hydronium ion. The hydroxide ion, this is what makes something basic. The hydronium ion, this is what makes something acidic. A lot of people think it's the H plus that makes things acidic. Well, actually, it's the H plus when it's attached to a water molecule, making the hydronium ion that makes things acidic. And we're going to be comparing acids, strong acids versus weak acids. Why is one acid strong? Why is one acid weak? It depends upon the formation of this molecule right here. And we'll get back to that later. So what makes this again? Well, what makes this is the H2O coming and getting an extra H plus, and this forms the H3O plus, or the hydronium ion, and this is synonymous with something that is acidic. I'm going to put that in parentheses. When we say something is acidic, we're referring to this H3O plus, but it's often just written as the H plus. So things that are acidic have this H plus, things that are basic have this OH minus. But really, when it's the H plus, it's H3O plus. It's the H plus that's attached onto the water. We lost lights. Okay, last thing we're taking a look at is going to be the concentration. We got a couple more items actually. Concentration of acids and bases. So these bracket symbols right here, this is used to symbolize the word concentration. So this actually means the concentration of H plus. This means the concentration of OH minus. So let's take a look at a couple of examples of the creating something that's neutral, creating something that's acidic, and creating something that is basic. So once again, we're going to be going through this scenario right here. We're not going to draw it, but we're going to create these molecules in the same manner. So if you take H2O and you put in some H2O, if you remember, they bump into each other. Very small amounts are going to be bumping into each other. This creates H3O plus OH minus. Okay, so let's take a look at the concentration of each of these. We have one water, okay, we have one here, we have one here. Let's put a 1 here. This is the coefficients. We have one here. It produces one of these, it produces one of those. So what we have here is we have the concentration of H3O plus, which again can be written as this, is going to be equal to the concentration of OH minus. And again, H3O plus you could think of as just H plus. So the H plus is equal to the OH minus. When the H plus is equal to the OH minus, that's when you have something that is neutral. Water is both an acid and a base, which makes it neutral. It's neutral because the concentration of acid is equal to the concentration of base. When this happens, it is neutral, meaning the concentration of the acid is going to be equal to the concentration of the base. And when this takes place, you have a pH of 7. Okay, let me go ahead and refer to what does pH mean. pH is equal to the potential, that's the P in the pH, the potential to hold hydrogen. Okay, so having a pH of 7, this is right in the middle of the pH scale. So there's very low potential for it to hold hydrogen, but very low potential to give it away as well. we're going to take a look at the potential changing when we make an acid or if we make a base. So let's take a look at acids. With acids, we're going to have, again, two waters. And this water will create H3O plus and OH minus. Let's now throw in some HCl, some hydrochloric acid. Okay, this was actually the red liquid, the red fluid that was using to check the pH and to change the color of the litmus paper as well as the Congo red inside the sponge. If we take hydrochloric acid and we add this to water, this is what's going to happen. Well, this H is going to be given to this over here in a bump, and this is going to give the H to the water as well. So the main concept of acids is acids give up their H pluses. They give up their H pluses. So here's the H right here. Remember, water is both an acid and a base, but this is hydrochloric acid. It only has an H to give up, and it's going to give its H to the H2O. What's it going to create? When this H combines with the H2O, we create another H3O plus. We're left with the Cl, and the Cl is going to be a minus. So let's take a look at this box over here. This is the end product of what we have now. We want to compare the concentration of H3O plus to OH minus. So the concentration of H3O plus, and we're going to compare the concentration of OH minus. So here's just water, okay? And here is when we add hydrochloric acid. What do we get more of? H3O pluses or OH minuses? We actually have two of these. We only have one of these. So the concentration of the H3O plus is greater. We can also say the concentration of the H plus is greater than the OH minus. When we have more acid than we do bases, this is acidic. We have more H plus. But while we have more H pluses, the pH is actually going to be less than 7. Let's take a look at what pH is, going back to the previous definition. pH is the potential to hold hydrogen. What do acids like to do? They like to give up their H's. So what is their potential to hold hydrogen? Well, they don't like to hold hydrogen. They like to give up the H plus. So the potential for acids to hold hydrogen is going to be a very low pH. Their potential to hold hydrogen is low because they don't like to hold hydrogen, they like to give up the hydrogen. Bases, on the other hand, these absorb H pluses. Let's go through a similar scenario. We have H2O plus H2O produces just what we have here, H3O plus and OH minus. Let's go ahead and add a base, which is sodium hydroxide. NaOH plus H2O produces, well, when you take NaOH and you put it in water, it actually falls apart. And it falls apart into an Na plus, and it dissolves, plus an OH minus. This is an ionic compound, and so it falls apart like this. And the water just stays the same. Nothing happens to the water. This forms your solvation spheres around your ions. So let's take a look, and we're going to analyze what's inside my box here. Here's the two waters. These, remember, they bump, okay? So that's transferred to there. So now we have an acid and we have a base. This just actually dissolves. It falls apart into an Na plus and OH minus. The water is not affected by this. Let's, though, compare the concentration of H3O plus and OH minus. Okay, I have 1 H3O plus versus 2. Which of the concentrations is going to be higher this time? In this case, the OH minus, because I have 2, is higher than the acid. So when the acid is less than the base, or the base is more than the acid, this is going to produce basic conditions. And it's basic because I have more OH minuses. And my pH is going to be greater than 7. Well, 7 is neutral. Okay, it's the middle of our pH scale. So if I have something that's bigger than 7, okay, my potential to hold hydrogens is more. Well, that seems true for bases, because what do bases like to do? Bases like to absorb the H pluses. So their potential to hold hydrogen is very high. Bases have high pHs. Acids, again, which give up their H pluses, their potential to hold the H pluses is low because they're giving them up. The potential for bases to hold the hydrogen is high because they like to absorb those H pluses.